Okay, good afternoon, everyone. This is Chen Zheng from Chalmers University in Sweden, Gothenburg. And we are working at the design of the power converter in Workbench 4. And today I'm going to talk about the modulation techniques for multilevel converters. And first, let's have a quick look of the general schematic diagram of a converter feed, variable speed pumped storage hydropower unit. And as we can see, the unit contains let me call the laser point. Yes, contains a hydro turbine or pump. It's a reversible turbine, which is generally a Francis turbine in this case. And it has been greatly studied in Workbench 3. And the turbine will drive a synchronous generator, which is connected to a power electronic converter. And the power electronic converter in this case is a back-to-back case setup. And it means it can convert the AC voltage from the generator to DC, and then convert the DC voltage to AC grid if we connect the power converter directly with the grid. And sometimes we can connect the power converter via a transformer to the grid. And this depends on the voltage level of the generator. And the core part for us at the Chalmers University is the power converter. And the objective is to design converter for this variable speed hydropower generation with up to 30 starts and stops per day. The large number of starts or stops means a frequently cyclonic behavior of the converter, and especially the temperature swings inside the converter. And this will have a great impact or effect on the lifetime of the converter. Therefore, we need to determine or study the losses of the converter. The core part to study the losses of the converter is the modulation techniques and also the converter topology. And therefore, in this project, we will study the modulation techniques and also the converter topologies. Okay, first, let's talk about the two-level converter. On the left side is a schematic of a two-level voltage source converter. It contains a DC link and 6 IGBT and diode pairs. If we on the right side is a one-phase voltage of the converter. If we turn on the up switch or the one phase, then we will get the positive half DC link voltage. If we turn on the lower switch, then we will get the negative half DC link voltage. And this is two level, as we can see, for one phase voltage. And this slide is about the NPC converter, which is called neutral point clamped converter, and it belongs to one kind of the multi-level converters as well. On the left side is a schematic of a three-level NPC converter, and we can see that the neutral point of this DC link is clamped by the diode 1 and the diode 2 here, and this is where the name neutral point diode clamped converter comes from. And in the middle is a three-level NPC animation, which describes the phase voltage of the converter. If the switch T1 and T2 on the upper arm are switched on, then we can get the positive voltage. If the switch T3 and the T4 are turned on at the lower arm, then we can get the negative voltage. If the switch T2 and T3 are turned on, then we can get 0 voltage. So basically, we can get three-level voltage by this electric diagram of the converter. On the right side here is a schematic of a 5-level NPC converter. It has the same topology as this 3-level NPC. However, as we can see, we will have more switches in here, for example, in one phase, we'll have 8 switch IGBT and diode pairs, while in the 3 level, we will have 4 switches. And also, we will have more clamped diodes in this 5-level MPC converter. And yes, this slide is about another converter, which is called modular multi-level converter. And in short, we can say it's MMC. And on the left side is schematic of N-level MMC converter. In each phase neck, we will have 2 times N submodules. And this submodule here can be a half-bridge module or full bridge module. But if we use half-bridge module, we will have less switches compared with full bridge. On the right side is 5-level MMC converter animation. If we look at this AC output voltage for one phase, and we can see it has 5 levels. Okay, here comes a question. Why do we need the multi-level converter? Well, if we look at the AC output voltage from 2-level converter and the 5-level converter, we can clearly see that the more the level the converter can generate, the waveform of the output voltage can be more sinusoidal, and which means it will have less total harmonic distortion in the voltage waveform. Plus, more voltage levels means we will have lower dV/dt on the motor winding stress. And apart from the above reason, more voltage level means more freedom to select the suitable power switches for the converter. If the DC link voltage is, let's say, 13 kilovolts for the medium voltage, and if we choose to use a 2-level converter, then we need to find a switch which can block more than 6.5 kilovolts. But for this 5-level converter, the power switch with the capability of blocking 2.6 kilovolt is required. And that means if we go to the market, we can find more choices when selecting the switches for the 5-level converter. But on the other hand, if we add, let's say, can we have the infinity, not infinity, but as more power, as more voltage level as possible, then we will bring the capacity to control the converter. And it will be an issue to do the modulation as well if we want to achieve lower power losses inside the converter. So the modulation techniques for different for converters can be divided into 2 categories: the sinusoidal PWM and the space vector modulation. For the sinusoidal PWM, it can be divided. It has let's say, especially for the multi-level converter, we can have this phase shift PWM or level shift PWM. And if we want to fully utilize the DC link voltage, we can have this third harmonics injection PWM as well. And for the space vector modulation, it can be divided into continuous and discontinuous modulation. For the sinusoidal PWM, if it's an N-level converter, that means we need at least N-1 phase shifted or level shifted PWM carrier signal. On the left side of this slide is a 5-level converter, and we can see we have 4 PWM signals here, and they are level shifted. And the modulation in for this case is 1. And if we want to increase the modulation to, let's say, 1.1, then what we can do is to use this third harmonic injection technique. So on the right side is modulation waveform for the third harmonic injected 5-level sinusoidal PWM converter. And the maximum modulation index can reach 1.15, which means 15% increasement in the modulation index compared with this case. And we still we can get sinusoidal output from the converter. However, to obtain multiple PWM carriers with specific amplitude shift or phase shift is quite hard with a regular microcontrol unit. Therefore, we prefer to use space vector modulation. And okay, what is a space vector modulation? Well, let's first introduce the converting from 3-phase to 2-phase or alpha beta coordinates. So on the top here is a 3-phase voltage. And if we multiply by this famous transformation matrix, and then we can get a 2-phase voltage, which in this case we call it voltage alpha and voltage beta. And if we put the voltage alpha beta into this alpha beta plane, then we can see it's a voltage rotating with this circle, on this circle. And one thing we should be mentioned here is if we look at the amplitude here for this sinusoidal voltage waveform, it's the same for both 3-phase voltage and the 2-phase voltage. And this is called the amplitude invariant transformation. In some other cases, we can use a power invariant transformation, and this matrix will have a different coefficient here, which is not 2/3 anymore. It will be some other value. Okay, this slide is about the voltage vector in the alpha beta plane. Take the 2-level converter, for example. Different switch combination can generate different voltage vectors. For example, if we look at this, if we turn on all the NOR switches in 3 phases of this 2-level converter, then we can get to the voltage V0. And we call it, if we look at this alpha beta plane, then V0 is at the origin of this coordinate. And if we turn on the up switch of phase 1, but we still keep the NOR switch of this phase B and phase C on, then we can get to this combination, which is called 100, and it stands for the voltage V1. And if then again we go to the alpha beta plane, and we can see V1 is here. So for the other voltage vectors such as V2, V3, here should be V4, V5, and V6, we can find different voltage vectors on this alpha beta plane, and it can formulate this hexagon. Basically, all the voltage vectors are at the point of this hexagon. So if we combine the alpha beta voltage and the voltage vector, so the alpha beta voltage is this inscribed circle, while the voltage vectors are in this hexagon. Then we can see the 3-phase voltages convert to 2-phase voltages, and then in the alpha beta plane, it is rotating on the inscribed circle of this hexagon. And then the hexagon can be divided into 6 sectors. Let's say if the reference voltage is located in the first sector, if it's here, and if this is the red line stands for the reference voltage, and if we want to synthesize this reference voltage, we can choose the voltage V0, V7, V1, and the V2. Each voltage sector with different time durations, then we can synthesize this voltage vector, reference voltage vector. And the next step is to determine the duration of each voltage vector. We can, by use the amplitude and also this theta or angle here, we can calculate the time duration. And once we got the time instance, we can send this time to the controller to control the gate to the switch on and the switch off. And this can be done by with the help of a sawtooth waveform to determine the switching actions inside the switch. Let's say if the time duration of V0 is TV0 divided by 4, then after this time instant, then we calculate the duty cycle of this, and we add another TV1 divided by 2, which is the time duration for this V1 voltage sector. Then we send this signal into the controller. Then we can control the switch opening and closing. This is for the two-level converter space vector modulation. And for the three-level converter, it will be the same case. If we remember that for this three-level MPC converter, we will have 3 states. If the both upper both upper switches are turned on, then we will get the positive voltage, and then we call it state 2. And for this case, if the switch in the middle are turned on, then we will get this 0 voltage, and we call it state 1. And if the lower switch is in the phase A is turned on, then we call it state 0. Then we put these different voltage vectors on this alpha beta plane again. Then we can create another hexagon, but with more layers compared with 2-level. So this is a hexagon for the 3-level converter, and it will have the 2 hexagon layers. And if we look at the origin here in this alpha beta coordinate, then we can see it has 3 switch combinations which can generate this switch this voltage vector. So these 3 voltage vectors, we can call it redundant voltage vectors. And these redundant voltage vectors can be used to, if we want to minimize the losses inside the converter, this can be used. And sometimes if for the MPC converter, sometimes the neutral point voltage, it can drift from the value what we want. So with these redundant voltage vectors, we can use it to control this neutral point voltage as well. For the 5-level converter, then we will have even more complicated hexagon here, and it will have 1, 2, 3, 4 layers of this hexagon, and we can see it will have more redundant switches states compared with before. So if we want to implement this in simulation or actual control unit, we need to find a solution to, or we need to find a general algorithm to do the trick. So what we can do is to transform this alpha beta coordinate to another coordinate, which is called 60-degree coordinate. Basically, 60 degree stands for 1 sector here. And if we convert it from this alpha beta coordinate to this 60-degree coordinate, then this switch states can be simplified, which is in this case 0, 0, 1, 0, 2, 0 in this. And the next step is we need to determine where the reference voltage is located. And for example, in this case, the reference voltage is located inside this small triangle. So we can use the voltage VE, VG, and the VF to synthesize this voltage, this reference voltage. And also, if we just look at this big triangle or this sector 1 here, we can find there are two kinds of triangle sequence here. One is like this triangle DEF. We call it the Noah triangle, while another one is like the triangle FEG, which is basically flipped of this Noah triangle. Then we can call it the upper triangle. So so basically the voltage, the reference voltage can be located in either in the lower triangle DEF or in the up triangle FEG. So then if the voltage is located inside this the lower voltage triangle, then we can synthesize the voltage with voltage D, voltage E, and voltage F. So the sequence will be from it starts from voltage D, goes to voltage E, goes to voltage F, and goes to voltage D again, and then goes back to voltage F, goes back to voltage E, and goes back to voltage D. Basically, it's written here. We start from voltage D to E to F, and to D prime. The D prime here means it's the same voltage vector compared with this voltage D, let's say here, but we use another switch combination. So basically that means if we start from 2, 1, 0 here, then if we goes back to D prime, then we can choose 3, 2, 1, another switch combination, but it will get the same voltage vector here. And the same sawtooth method can be used to generate the time instance or to get to the time instance to control the opening and the closing of the switches inside the converter. So this is a typical space vector modulation for a multilevel converter. Then an interesting thing is called the discontinuous PWM. And by using the discontinuous PWM, we can decrease the switch, the losses, especially the switching losses inside the converter. And if we look at this this sawtooth waveform, which we use to determine the switching signal inside the converter, then we can see it's we will have 7 segments here. Basically, this D prime is the same vector as this VD. So the general idea of discontinuous PWM is to remove these 2 D prime vectors here. So we just use the voltage D and the voltage E and the voltage F, but we can synthesize the voltage, the reference voltage here. So if we take the 2-level converter, for example, if the voltage reference is here is in sector 1, and if we use voltage V0, voltage V1, and voltage V2 to synthesize this reference voltage, then the voltage will start from V0 to V1 to V2, and goes back to V1, then goes back to V0. And then we can see the voltage is clamped to V0. And if you remember, in the previous case, we said voltage V0 means all the switches, all the lower switches in phase A, phase B, and phase C are turned on. So that means the converter now is clamped to the negative rail of this DC link. So this is called discontinuous the PWM mean. And on the other hand, we can use voltage V1, V2, and V7 to synthesize this reference voltage as well. So this is called DPWM max, and in this case, all these three phases are clamped to the positive rail of this DC link, and this is called DPWM max. On the right side are the switch signals, which generated from this. The up one is for the discontinuous PWM mean, and the lower one is for the discontinuous PWM max. And there are some other kinds of discontinuous PWM as well. And on the left side of this slide is called discontinuous PWM1. And the difference compared with before is we can see the each phase or each switch is clamped to the positive, and here negative rail of this link alternately in one switching fundamental period. In the previous slide, if we look at here, for the DPWM mean, the converter leg is always clamped to the negative DC rail in one fundamental period, while in the DPWM1 it will alternate in one period. And if we change the sequence of the switching, then we can get another another DPWM method, which is called DPWM3, and we can see we can see that each phase is clamped to the positive DC rail and negative DC rail just for 30 degrees, and it will alternate in after one inside one switch fundamental switching period. And it is studied that this DPWM1, it will have more even loss distribution among all the switches, because the clamped states are alternated in one fundamental period. So for the multi-level converter, we can choose to use this method as well. However, if we look at the hexagon, the voltage vector hexagon of three-level converter, it looks like this. And the first step is we need to determine this in which region or which zone we want which phase to clamp to which state. So as we talked before, there are three states inside in each phase, so state 2, state 1, state 0. For example, in this small zone, we want the phase A to clamp to state 1. And in this small zone, we want the phase A to clamp to state 2. And in this way to cross this border, then we want the phase C to clamp to state 0. So by selecting the by designing the switching states inside each small zone, then we can create this DPWM1 pattern inside this three-level converter. If we look at the right side, this is switching or get signal from when we run this DPWM1 simulation. And here we can see that the switching for this switch T1, it will keep clamped to this positive rail for this period. And for this switch T2, it will clamp to the positive for this period. But if we combine these two, T1 and T2 together, then this upper arm of the switch will clamp to the positive rail of this link for this small period. And for this 5-level converter, we can use the same method to achieve the DPWM1. And by dedicating which small zone should have which clamped state, then we can get to the DPWM1. On the right side is a gate signal in one phase of this 5-level converter for different switches. So if we jump back to our target in this project, which is to design a converter which can have up to 30 starts and stops a day. And that means we need to have this, if we have different converter models and we have different modulation techniques, we can create a different power electronics loss map. And from the power electronic loss map, if we apply the mission profile, which we can get from workpack 2, then we can create, or we can get the junction temperature inside the power converter. And once we got the junction temperature profile, we can use a rain flow counting method or algorithm to calculate the lifetime of the converter. And by comparing different models, different modulation, different topologies, then we can determine which one is most suitable for our case and which one can have the most optimal lifetime. Okay, that's all on my presentation. Thank you very much for your attention.
Thank you. Are there any direct questions to this presentation? Yes, go ahead, Torbjörn.
Yeah, I could ask Cheng Jung. So do you have any hypotheses of how much you can smoothen or change the temperature variations within a multi-level converter? Can we reach 1 or 2 or 3 or 4 years more lifetime?
To be honest, it's hard to say to get a specific number, but if we use DPWM, especially for the multi-level converter, the up switch, especially for the alternator of the switch, which is inside the alternator, it will decrease around maybe 15%. Okay, so that means the
yeah, it was
lifetime
an impossible question, but yes.
Yeah, but I mean, at least in that sense, the lifetime for that specific switch can be increased. Yes.
Just more of curiosity, but at the moment you are mainly simulating these different topologies, or are you also doing laboratory testing or something, testing them and implementing them on small devices?
At this moment, we are still running the simulation, but soon we will have this lab test. We are building our prototypes to do the experiment.
Bo Hannes here. I'm also wondering, you're speaking about lifetime. For me, is that 40 years, or is that 10 years, or 1 year? What is the span? I mean, because I'm thinking about in hydropower, our customers expect very long lifetime of components. So that's the reason for my question.
Yes. Well, it depends on the mission profile or the load profile of the the power the converter which needs to generate, and also it depends on the variations of from the mission profile. If we have more variations, then the lifetime can decrease more compared with very stable power generation. But the general lifetime of a converter, I think to be honest, I'm not quite sure about the exact number.
Not an exact number. I was just a fingerspitzgefühl, a fingertip.
Yeah.
Yeah, but for sure we want to keep it as I think 10 years is out of question.
Yeah. I think in car application, then maybe it's around 20 or 20 years.
Yeah,
could be. Yeah.
But maybe one could mention that an advantage with the MMC setup that Cheng-Jung showed is that then it's possible to operate with one failed, and then one can do a kind of maintenance and change those that fail.
Yes, exactly. Yeah.
But otherwise, of course, I think that if possible, we would like to have it as long as the generator, or maybe one could have it half the generator time and change it in between. But we haven't thought of it so much. A good issue.
No, it's we face quite often that a lot of the mechanical parts should be able to survive 80 years.
Yeah, I think that for power electronics that is too ambitious. So
I understand.
So I think exactly as with cars, then some things you change after a while, like the camrem, whatever that is in English, and or oil, and some things you think last all the time. But perhaps one change could be a good choice.
Yeah, good.
We have two questions here in the chat room. I'll leave the one question regarding industrialization to after when you start with the discussion. But there was a specific question: how much losses can be reduced with the DPWM versus the SVPWM?
Well, I'm still running. I haven't got to the I haven't finished the simulation results, so I cannot give an exact number about that.
Maybe I can help here, Cheng-Jung, a bit.
Yeah.
We did an earlier work here at Chalmers with a pump drive, and okay, I cannot give exact numbers, but the one very good thing is that you can keep the switch that has the highest current without switching. So, but it was a substantial amount. Could it be up to 30% of the switching losses that could be saved? So it is really important. The drawback is when you use it in a vehicle, the drawback is mainly the noise emission. But I think that this is perhaps not an issue in a hydro turbine converter being very remote.
Oh, I think you're right there. I think there is other sources.
But of course, to some extent also, we do emit low frequency harmonics, but I don't see that they would be doing so much harm.